It is part 2 of section 2.4. In the first part, we try to find linear factors of polynomials by using the Horner's method. Here, we'll try to find the quadratic factors of polynomials by using Bairstow's method. From quadratic factors, we can decide complex valued rules. Here we have a polynomial of degree n. For the polynomial, if the polynomial is of real coefficients, so all coefficients are real, and if z is a non-real root of p, then z bar, complex conjugate of z, is also a root n. The product x minus z and x minus z bar is a real quadratic factors of z. Now here we have polynomial factorization theorem. If the polynomial is a non-constant of real coefficient, then it can be factorized as a multiple of linear and quadratic polynomials of real coefficients. Once you try to factorize along with the real coefficients, then partly the factors must be quadratic. If we want to go all linear, then some portion, some linear factors will have the complex values. Okay. Now here we start how to find quadratic factors. We will try to find quadratic factors of form here x squared minus ux minus v. Then once the given polynomial of degree n is divided by the factor, then quotient will come out and remainder. Here, this is quotient whose degree is n minus 2. We formally write down in this way. And now remainder term must be linear. We write down in this way. Rather than ax plus b, we write down in this way. Later on, this will make very convenient the recursive formula like that. And we plug these two on the right side, and we try to match the coefficients of the powers of x. Then we can get that recursive relation, so that for each n here, each k, you can get an equation so that we can write in this way. Earlier, when we tried to find the linear factors by using the Horner's method, and we try to get such a similar formula. Now, here, because we have u and v, two terms here, so the recursive formula is a little more longer, right? Okay, but same principle. Just try to match the coefficients both sides, and we get this formula. Okay, now the Bairstow's method is start with here observation. Okay, when for example, this one is a factor, then now r of x must be 0. It is possible when b1 and b0 are simultaneously 0, then remainder is 0, and here it becomes the quadratic factor. However, b0, b1, here last two are dependent on u and v. So we may consider B0, B1 as functions of U and V. Okay, here now. Okay, that is exactly here. So we have to find and we have to update B0, B1 such that eventually they should converge to 0. Now that is happening for given UV, and after here finding correction terms, correction vectors for U and V, and we have to make B0, B1, 0. So here, exactly same as for the earlier for linear factors. Here we linearize, and now by using tail expansion. So that is with respect to now here around UV, along with this perturbation, we make a linear expansion, and from second order we ignored. And if we collect these four, then that is a Jacobian. And then now, so the Jacobian delta U, delta V is the same as now negative of this, the function vector. So that is exactly this one. So after solving this system, delta U, delta V is made, and now we can update UV. And now running iteratively and try to update here UMV such that once we try to, for given UV, try to evaluate by using this recursive formula, then B0, B1 must be 0. If these two are 0, then the current UV will make a quadratic factor, right? Okay. Okay, that is a Bairstow's method. Now here, to get, now the thing is, we have to find these derivatives, Jacobian. To make the Jacobian, now we start with here some definitions, the terms. We define the derivative pk. Now u derivative is ck. Now pk minus 1, v derivative is dk. We define this way. In fact, the derivation from earlier in this portion is now given by the Bairstow in his book, Applied Aerodynamics, in 1920, published. In the book, it is given in this way. Then, here, if you differentiate the recursive formula, this one, with respect to u and with respect to v, and then use the definition here now, then you can reach these two equations. Now, we can see easily that Cn plus 1 and Cn plus 2, also for d variables, dn plus 1 and dn plus 2, these are 0, and these two formula is identical, except C is replaced by D, which means that CK, DK, the two sequences are identical. So we can focus on only one sequence. So here, now the Jacobian is B0, B1, CV derivative, so that it can be written in this way, C0, C1, C1, and C2. So here, delta U, delta V, and Jacobian inverse can be easily gotten, and this one. Now, once you try to get, by using this recursive formula, and see, then Jacobian can be easily gotten, and by using delta U, delta V, you can update U and V, so that along with the update UMV, now B0, B1 becomes 0, then that's the final answer for UMV, right? Okay. Now this is Maple implementation. So a major part of the code is around there. That is now updating B value and C value along with one loop. And then that is now after finding the determinant of J and delta U, delta V is made and UV are updated. I implemented this code along with some detailing rather than vector form. Okay, that is the major part, and remaining parts are, these parts are printing out. Let's see here. For the polynomial, here first we check the degree and we try to get coefficients. Now from 0 to n, we try to get coefficients. And number of iteration, the maximum number of iteration is given 10, and tolerance is 10 to the minus 10. And for the polynomial, we start with u is 3 and v is minus 4, that is initial value. And here, okay, that is uv value, and that is delta u, delta v value. Okay, so eventually, this delta u, delta v value is the difference between consecutive iterates. So here, that can be used as stopping criterion. Now, after 7 iterations, here look at u and v are converged here, and then these are delta u, delta v. So it converged. And after 7 iteration, that's quotient, and remainder is now, that is b1 x minus u plus b0. Okay, they are small. And then here quadratic factor x squared minus ux minus v. Okay, that is u and that is v. And from this quadratic factor, we can find 2 zeros, 2 complex valued roots. They are here. So by using Bairstow's idea, which are a kind of generalization, expansion of the Horner's method, and by using that, we can find quadratic factors, and out of quadratic factors, we can decide 2 complex the roots. Okay. When we try to get the roots of a polynomial of degree n, then we can use Newton method and to find one linear factor. And now by using so we can find a linear factor, for example, and the Q1. Now from Q1, again, we can find another linear factor and Q2. And from Q2, another linear factor or quadratic factors. And in this way, from the given original polynomial, we try to find a factor, linear or quadratic. And by using the quotient, again, we try to find another factor, another factor. In this way, we try to find the factors. This procedure is called deflation. So finding zeros of a polynomial is a kind of a deflation. Through this deflation procedure, people are trying to find the polynomial zeros. Okay. Now here, for each factor, we are using Newton method, and then also from quotient we try to another one, so that here in an approximate 0 x k plus 1 hat of qk will generally not approximate a root of p0. In fact, this factorization will include an error, and for the error, one more factorization will make add one more error, so that later on, if you find x1 hat to xn hat, then later on error will become larger. For instance, you may start with, in the beginning, 10 to minus 12 accuracy, but for the last one, and around xn hat, the error may be around 10 to minus 6 or 10 to minus 7, so that compared with the earlier error level, and later on error level is much larger. So to make all the solution accurate, we apply one more time the Newton's method, starting with this x hat values. X hat values are yet accurate, but compared with the required accuracy, it has some large error. However, yet accurate, so that start with these zeros, we can apply Newton's method and using the original polynomial. So rather than here q in the quotients, later quotients, we are using original polynomial to update the accuracy of these zeros. In modern society, the software is made that way. Start with the deflation, and the solutions will be now updated by using the Newton's method with the original polynomial. So then now that is accurate enough. Okay, that's the end of the section and end of the chapter. Thank you.